So we're going to start by doing a couple of examples of the fundamental theorem of calculus and how it's used. First, let's evaluate the integral from pi over 6 to pi over 2 of cosine x dx. So what we do is we find an antiderivative of cosine x. We know that sine x is an antiderivative of cosine x. How do we know that? Because we know that the derivative of sine x is equal to cosine x. So that's what it means to say that it's an antiderivative. If you've been paying attention for the last couple of sections, you know that sine x is not the only antiderivative of cosine x. So, for example, is sine x plus 1, or sine x plus a million, or sine x minus a million. It actually doesn't matter which antiderivative we use for this purpose. Any of them will work as long as we use the same one throughout the problem. So it's sort of customary to just choose the simplest antiderivative, in other words, the one where the plus c turns out to be 0. So even though, strictly speaking, the entire family of antiderivatives of cosine x is sine x plus c, we just use the one where c equals 0, and we're just going to use sine x. Okay, so given sine x is in fact an antiderivative, what we do is I'm going to write this integral again, pi over 2 cosine x dx. This is equal to sine x from pi over 6 to pi over 2. This bar that we write means that we're going to now take the antiderivative and plug in the two endpoints and subtract. So it's a little bit different from the integral sign in that before we find the antiderivative, we put the integral sign there. But what we're asserting is that this definite integral here is going to be equal to this subtraction problem using the antiderivative that we found. So we're going to expand this again. We're going to plug in the two endpoints and subtract. This is going to be sine of pi over 2 minus sine of pi over 6. That's going to equal sine of pi over 2 is 1, sine of pi over 6 is 1/2, and the answer is 1/2. Now, what's the interpretation of this? Here we have the cosine function. It looks like this. And on the interval pi over 6 to pi over 2, which is roughly, that's pi over 6, and that's pi over 2, what we did was we found the area under the cosine function on that interval. So that's the interpretation of this, and we found that that area is 1/2, and we did it using the fundamental theorem of calculus. Okay, so let's do another example. Let's evaluate the integral from 1 to 4 of the function 3/2 root x minus 4 over x squared dx. First thing to observe is that we should, in order to use the power rule to find antiderivatives, we should rewrite the radical and the reciprocal as a fractional power and a negative power. So this is going to equal the integral from 1 to 4 of 3/2 x to the 1/2 minus 4x to the negative 2 dx. We now find the antiderivative, and that's going to be 3/2 times x to the 3/2 over 3/2 minus 4 times, this is going to be x to the negative 1 over negative 1. And when we have a sort of a compound function, we have a compound antiderivative that involves several terms. Instead of using that line that we used in the last problem, we put them in brackets and write the limits of integration out here. So note, there's no more integral sign because we already did the integral. We found the antiderivative, and we're just indicating in this compact form what the subtraction problem is going to be. I want to simplify this expression a little bit more before I start plugging in numbers. So let's observe that these 3/2 over 3/2 just cancels out, and we also have minus 4 divided by negative 1, which is going to give positive 4. So that gives us x to the 3/2 plus 4x to the negative 1 from 1 to 4. So that's going to give us, let's see, it's going to give us 4 to the 3/2 plus 4 times 1 over 4. So this is the part where I plugged in 4 into the antiderivative, and now I'm going to subtract. I'm going to plug in 1. That's going to be 1 to the 3/2 plus 4 times 1 over 1. And I'll just do a little simplification here. 4 to the 3/2 is 8 plus 1. And then we have minus 1 plus 4, so that's going to be minus 5, so I have 9 minus 5, and the answer is 4. So that's the value of that definite integral. Okay, so another example, we're going to find the integral from 3 to 5 of 1 over x plus 1 dx, which I've written in this more compact form with the dx just in the denominator. Just recall that 1 over x plus 1 dx is the same thing as just writing dx over x plus 1. So that's why I can write it that way, and you should get used to that notation. So the first thing to observe is that the derivative, I'll write this in a different color, is the derivative of ln x plus 1 is equal to 1 over x plus 1. We could have done that by the chain rule. So we know that ln of x plus 1 is in fact an antiderivative of 1 over x plus 1. Therefore, this integral is just going to be ln x plus 1. I should actually say the antiderivative has absolute value around it, although it's not going to matter because I'm just using positive numbers 3 and 5. I'm plugging positive numbers in, so it won't matter, but let me just be a little bit formal about this. So this is ln of x plus 1 going from 3 to 5. That gives us ln of 5 plus 1 minus ln of 3 plus 1. That equals ln of 6 minus ln of 4. I'm going to write this in a little bit more compact form. That gives us ln of 6 over 4, which equals ln of 3 halves. That's sort of the form that I like, although it would certainly be reasonable to write ln of 6 minus ln of 4 or ln of 3 minus ln of 2. Either of those would be valid answers. So for our next example, let's evaluate the definite integral from negative root 3 up to 1 of the function 1 over 1 plus x squared. Now, the thing to recognize here is that we already know that the derivative of arctan x is 1 over 1 plus x squared. So it's certainly correct to say that that an antiderivative of 1 over 1 plus x squared is arctan of x. Therefore, we can simply use arctan of x as our antiderivative, and we're going to let that go from negative root 3 up to 1. So this is going to be arctan x of, sorry, we put in the top one first, arctan x of 1 minus arctan x of negative root 3. So part of the point of this exercise is just a refresher on the values of the inverse trig functions that you know. The angle whose tangent is 1, and you should know that, good review as we start to approach the end of the course in the final exam, know that arctangent of something, the arctangent of x means that the angle whose tangent is x. So arctangent of 1 is pi over 4, and arctangent of negative root 3 is negative pi over 3. So that's going to give us pi over 4 plus pi over 3. Common denominator looks like it's going to be 12, so that'll be 3 pi plus 4 pi over 12, which is 7 pi over 12. There we go. So that's the so that's the definite integral of this function 1 over 1 plus x squared on the interval negative root 3 up to 1. I just want to write this a little neater before I pause. There we go, 7 pi over 12. Okay, so I want to do just an example that's just a little bit more complicated, just because we've so far had integrals of functions that were entirely positive on the interval of integration. This function dips into negative territory a little bit for its interval of integration. So here we have the integral from pi over 2 to 5 pi over 3 of sine x. So first we need an antiderivative of sine x. The antiderivative, or rather an antiderivative of sine x is negative cosine x. We know this because we know that the derivative of cosine x is actually equal to negative sine x. So what I need to do is I need to flip this around and say the derivative of negative cosine x is sine x. So we had covered this in the initial section on antiderivatives, that the derivative of the antiderivative of cosine is sine. The antiderivative of sine is negative cosine. So our antiderivative is negative cosine x, and we're going to let this go from pi over 2 to 5 pi over 3, like that. Okay, so what we need to do is we're going to find negative cosine of 5 pi over 3 and subtract from that negative cosine of pi over 2. Okay, so, alright, so what we have here is we need the negative cosine of 5 pi over 3. Cosine of 5 pi over 3 is negative 1/2. That's just one of the basic unit circle values that you should be able to recognize. So this is going to be negative 1/2. And then we subtract from that, this is going to be minus. Cosine of pi over 2 is 0, so that's going to be minus 0. And the answer to this is 1/2. Okay. Now, so what is the geometric interpretation of this? Let's draw this graph for a minute. So what we have is we have sine. If the graph of sine looks like this, let's go a little further out there. So that's 2 pi. This is pi over 2. That's pi. And so I'm going to put 5 pi over 3 is about there. So let's look at what we added up. We added up this area. I'll do this one in green because it's positive. And then we also there it is. We also subtracted this area. So once we did that, these don't quite balance each other out, but once we did that, we just got 1/2. So I just want to demonstrate something to show you what happened. We got with what we got when we integrated sine x from pi over 2 to 5 pi over 3 was we got a total signed area. In other words, we got whatever the sum was of this green positive area and then minus this pink negative area. That's becomes sort of fairly clear if I show you what I had done. So if I show you what would happen if I instead did the integral from pi over 2 to pi of sine x dx. So that would be, in other words, just the green area. So that's going to be negative cosine. Sorry, I want to do this in purple. That's going to be negative cosine of x from pi over 2 to pi. So that would give us negative cosine of pi minus negative cosine of pi over 2. So negative cosine of pi is negative 1, so that's going to be negative 1 minus cosine of pi over 2 is 0, so that would be negative 1 or positive 1. Now, this is the significance. If you notice, I'm integrating in the first example that I did, I'm integrating over a longer region, and yet I'm getting a lower number. The reason is that this method of finding the definite integral takes into account everything that happens, positive and negative, as we continue to add up the signed area. So you see what's happening is I started pi over 2 here, I move to the right, and the curve is positive, so I'm adding up positive area. Then I get to the point pi, and suddenly the curve dips below the x-axis, so now I'm subtracting area that's enclosed between the curve and the x-axis, because that's how we interpret signed area. We have the area between the curve and the x-axis that's below the x-axis gets subtracted from the whole pile of area that we're adding up. And the sort of remarkable thing about the fundamental theorem of calculus is that it takes all this into account automatically just by looking at the two endpoints. So it makes perfect sense that when we integrated over this longer interval, we got 1/2 because we were doing some adding in the green region and some subtracting in the pink region. When I instead integrated over this shorter interval, I only was integrating in the green region, and this method somehow knew that, and it failed to subtract this extra little pink area, and we got a higher number. So that's, this is really what the fundamental theorem of calculus is doing. It's adding up not so much area, but signed area. It's taking into account which regions are above and below the x-axis.